It's Nino Latimer, and this is my test 3. I had problem 3.28. Once again, I have another recurrence problem. In this case, we have a of 0 equals 1, and a of n equals a of n minus 1, plus the floor of the square root of a of n minus 1 for n is greater than 0. What is the goal of this problem? The goal is to find a closed form equation for the recurrent equation. Where would we start is we could start by laying the terms out and just looking for patterns and going from there. A good amount of terms here. Just based on the fact that our recurrence includes the floor of the square root of a of n would tell us that our number is going to be increasing by the highest perfect square under that number. So, for example, when a of n equals 1, starting at n equals 0, up until when a of n equals 4 at n equals 3, it's increasing by 1 increments. And then from 4 and beyond, it now increases by 2 increments, or the square root of 2. So the floor of the square root of 6 and the floor of the square root of 8 and the floor of the square root of 10 are 2. And it continues to do so until 9. So until n equals 6 or a of n equals 10. And that would be the most important pattern here to find. And we can move on from there. Initial thoughts on our closed form equation for this recurrence is that at the very least, it's going to be quite difficult because, well, first thing to notice is that our terms are increasing by increments of the highest perfect square root under that number. But that's in terms of a of n. But in order to, but our closed form equation will be in terms of n, the nth term. So yeah, we have to convert it from in terms of n to in terms of a of n. That would be the start, and then we'd have to go from there. So it's seeming quite difficult. I was just spitballing and kind of practicing here. So I know that if this was possible, that it would probably include the floor of the square root of n, though again, that's in terms of n, so I'm not sure. I went ahead and tried parentheses n minus the 4 of square root of n, parentheses, times the floor of square root of n plus L. I was just throwing stuff out there. That one was actually quite close. And typically, like the first 3 terms, L ends up being plus 3. So it was looking like we had something there, but then it'd be like after the 2, you end up with a 3. But in the next group, after the 2, you end up with a 2 or a 1. So the changes in L weren't something you could really predict in a way that you would have in a function here. So, said, the next thing to ask is a closed form possible? And considering we're supposed to be solving a recurrence, I would say, it has to be. That's what solving a recurrence means. However, if you take a look at the solution in the back of the book, it itself isn't a completely closed form equation. So it also it deals with knowing certain values of the recurrence itself, which can only be found by laying out the terms of the recurrence, which is kind of goes against the whole idea of a closed form equation. So I guess from there, I went ahead and came up with my own thing that was similar um, to the best of my ability. Right from the start, we noticed that whenever uh, a of n passes a perfect square, that the terms now start to increase by the square root of that perfect square until it reaches the next perfect square. So from there, we could say that when a of n equals m squared, that a of n plus l equals m squared plus l times m. And that would mean that when it's a of n plus 1, we have m squared plus m. For a of n plus 2 is m squared plus 2 times m. After that, we could say that if a of n equals m squared plus k, that a of n plus 1 would equal m squared plus l times m plus k. And that also works for perfect squares itself, because k could just equal 0. And that would be it for that solution. So for the textbook solution, they simply only use a of n equals m squared, as opposed to my a of n equals m squared plus k. Doing this allows you to, there's much less perfect squares within the a of n terms than there are numbers that pass perfect squares. And this allows you to have to know less a of n values from the recurrence to be able to use to find other values without solving the whole recurrence out. So with that being said, they have the solution to a of n plus 2k plus 1 equals m plus k squared plus m minus k. Then a of n plus 2k plus 2 equals m plus k squared plus 2m, as well as a of n plus 2m plus 1 equals 2m squared. And once again, you're still required to know some of the recurrence values, which defeats a closed form purpose. But along with that, we also have a of n minus 1 equals 2 to the power of l plus the floor of n minus l divided by 2 squared. And where l is the groups that the a of n terms fall under. For a summary, it would appear to me that a true closed form equation, it's not possible or it's not very probable. By knowing which terms are perfect squares, we could write that a of n equals m squared plus k, and then we have the solution a of n plus l equals m squared plus l times m plus k. And that's our final semi-closed form equation. That's all. Thank you.